Professor Doron Zaberger, who will speak about the narrow-minded attitude of contemporary mathematicians. First, a warning. This is not a proper math talk. There is a cliché that goes back at least to Halmos that says that every mathematics talks to have at least one proof. This talk will not have any mathematical proofs. It will have proofs, but not so-called mathematical proofs. And also a disclaimer. I'm going to talk partly about mathematics and partly about meta-mathematics. The mathematical part is joined with a brilliant young mathematician, Drew Searles. And the paper that is the inspiration for this talk was joined with him. But the meta-mathematics is not necessarily his views. Unlike me, who have a vengeful personality, he's the nicest, peaceful person in the world who cannot resent anybody, who is very, very forgiving. So all my ranting and raving is only due to me and probably is not shared by him. So I have to make it clear. And also any possible enemies that I may make from this talk, because it's going to be hopefully in YouTube in a few days, thanks to Eddie Knack, should be only directed at me. He is completely away from it. So this talk is partly a diatribe, but more appropriately a disappointment. My public disappointment at certain people whose name I will shortly. And a request for apology. It's never too late to apologize. So I want the people I'm going to mention here by name. It's not never too late. I'm going to post it also as an opinion and with a request for apology. And I promise you I'll forgive you if you will publicly apologize and say, I was wrong, I made a mistake. I make lots of mistakes. When I grade for a calculus class, often I make grading mistakes. Sometimes trivial one, sometimes most often one. Then a student has the right to appeal, and they write me in writing, and this is, you didn't take enough partial credit, and then I look at it, and very often I change the grade. So the same thing here, it's not too late to apologize. Let me start another disclaimer, and sorry, a warning. I'm going to do lots of analogies. Mathematicians like analogies. So I do analogies to things much more important and much more serious crimes than getting a paper rejected. So I'm not implying that this, unfortunately, but not terribly tragic, fact that a certain very good paper got rejected by 3 journals is a major tragedy. As I said in the abstract, it's really a case study. And I'm sure there are lots of other things like this, but people are afraid to speak up because they're embarrassed. For a long time, women suffered sexual harassment and even rape because they were embarrassed to report. And only lately, the former president of Israel, Mr. Katsav, is now serving a 7-year prison term for alleged, and I'm not sure, he denies it, sexual harassment and even rape of employees. And for a long time, and who knows how many presidents, former presidents, deserve to be arrested before, but they didn't get arrested because people were embarrassed or afraid or were too nice to complain. So another thing in mathematics, I get lots of emails because people know that I'm mad at the editorial system, but papers get rejected. I get countless of emails from people, excellent mathematicians, top-notch mathematicians, who tell me about unfair referee reports. But they keep it to themselves because it's still a stigma about being get rejected, even if it's unrightful so. So another case study is here. Get out of the closet if you think the editor or the stupid referee made a mistake. Post it in your homepage. Tell everybody the stupid. Unfortunately, the referee is anonymous. So the editor should be responsible for this. And you can always appeal to the editor. And in my case, I appealed to the editor, and the appeal was declined, not surprisingly. So let me start with a historical analogy. Whoever heard of the following man? Mr. J. Fraser Harrison. His impact to mathematics is very, very substantial. Unfortunately, has unintentional, not intentional, has unintentional impact to mathematics, negative, unfortunately, is very, very substantial. Does anybody know who this gentleman is? I'm surprised if you ever knew. Yet he is a very significant person. Unintentionally, he deprived of mathematics of many, many beautiful potential insights. He was the judge in Manchester, or near Manchester, who very, very humanly and liberally, instead of putting Alan Turing in jail, he suggested, and Alan Turing accepted, a hormonal treatment. And he was arrested and then convicted on gross indecency. And Mr. J. Fraser Harrison was not a bad man. He was just a man of his time, the early 1950s. In fact, he was ahead of his time. If you Google him, you only get 7 mentions. And one of them will get mentioned before the famous trial in 1952, where Alan Turing got convicted, and this led to a very, very bad hormonal treatment that made him depressed and famously led to his suicide at the age of 42, and deprived mathematics of many, many potential insights. In addition to being a personal tragedy, if instead of Turing, it would have been some nobody, it would have been equally bad. Humans are humans. So it's a personal tragedy here, and also tragedy to mathematics. Of course, it was unintentional. So if you Google him, what I found from 1949 from a paper called, I don't know, something straight. Judge Fraser Harrison said in the Liverpool divorce court, even ordinary, decent wives sometimes commit adultery. At the time, he was ahead of his time. That was shocking that a decent woman can commit, a decent wife can commit adultery. So he was not a bad man. He was still, but he was not, but he believed at the time that homosexuality was a gross indecency and there was a crime, so you cannot blame him. He did his job. The only thing you can blame him that he lived in 1952 and he had the attitudes, the wrong attitudes, I hope that you agree with me now, of people who lived in Great Britain in 1952. So I cannot really blame, personally, the following people. George Andrews, a very good friend of mine, collaborator too, who I admire very, very, very much. He's one of the greatest combationists of all, of at least of this era, okay, not of all time, but at least of the 20th century and early 21st century, and great number theorist. A nice person, very, very nice person. So I really like him. But his only crime that he belongs to this era and has a mathematical prejudices, and hang-ups of the late 20th and early 21st century. In fact, he's slightly leaning towards the mid. He's a little bit more conservative. And I think that George, you hear me? I hope you're gonna watch it. I admire you very much, but you made a very, very big mistake by rejecting the paper, you know what I mean, by Sears and Zalberger to the proceeding of the National Academy of Science. This is a very prestigious journal, and when people have an important discovery, they believe they did a breakthrough, they submit it to a member of the National Academy of Science, and if he or she think it's worthy, they process it. But George refused to even consider it. A priori, he said, it's not was it? It's not suitable for the PNAS. It's probably suitable for other journals. It didn't say it without merit, but George Andrews says it's definitely a priori without even looking at it, because the title Clay already admitted it's a non-rigorous disproof. I'll tell you later on what I talk about the subject. We wrote very politely, almost certainly. But we really lied. We say the Rademacher conjecture. The Rademacher, I tell you presently, the Rademacher conjecture. And then in very, very tiny font, you put almost certainly false. And this is not I was nice, I agreed for this. I did qualifying remark. We lied! It's not almost certainly false. It's certainly false. We do not have a rigorous proof that it is false. But it's still certainly false. Well, maybe not certainly, but as certainly as can be. Much more certain that George Andrews exists. George Andrews may just be in my dream. May just be a character in a video game with some hacker in some galaxy. There's no form of proof that George Andrews exists, or for that matter, Don Tabaka exists. But as certain as this. So he confused. So this is the problem with modern mathematics. They confuse two things. Knowledge and rigorous proof. Knowledge means justified. True belief. We know not everything is rigorous. But with mathematicians with a narrow-minded attitude, they think the truth means rigorous proof. Rigorous proof is an artificial game, nice game, fun game maybe for many people. Even for me sometimes I like to have sometimes rigorous proofs. But it's not an artificial game and has nothing to do with truth or certainty. This proof of the Rademacher conjecture, the probability that it is true, is much, much larger probability that Fermat's theorem is true. Andrew Wild's proof is probably correct, but it's just human proofs. It's not very possible, but it's somewhat possible. There is some mistake in it. So this is about the attitude of this. So going back to Fraser, Harrison, he deserved to be shot, but he never got shot. But something close to it got shot. So if you Google, there was a retirement party for another judge in Liverpool, and this guy once got shot by one of the people who convicted. And he tried to shoot him. Luckily, he did not get hurt. He escaped it. But he said, I still have the painting of the picture of Judge Fraser Harrison in my room with a bullet hole through it. So somebody who tried to shoot another judge months later, when Fraser Harrison was already dead by now, it was a recent thing, shot his picture. So this guy, who was very influential, barely you can see him. In most accounts in Wikipedia, it does say the judge. So I hope that George Andrews, although his crime is much less, admittedly, much less than Fraser Harrison in biology, also at least get a record, be on record, that he rejected a beautiful, very, very interesting paper to the proceeding of the National Academy of Sciences. But now let me pause and tell you the substance. Why is it so excited? Hans Rademacher, by the way, he was George Andrews's academic father. One of the greatest number theorists of the 20th century. And he is famous for many things, rightfully so. One of the things is the formula that got George Andrews into mathematics. In a NOVA program about partitions, He said that when he saw the so-called Hardy-Ramanujan-Rademacher asymptotic formula for the so-called integer partition, he fell in love with mathematics. It's an asymptotic formula. So let me tell you what it is. P of n is the number of integer partitions of n. This goes back to Euler. In particular, for example, P of 4 equals, let's see, 1 plus 1 plus 1 plus 1. 3 plus 1. 2 plus 1 plus 1. 2 plus 2. Anything I missed? That's it? No, one more. 4. The number of elements. 1, 2, 3, 4, 5, 6, 5. It's well known and easy to see. There's a nice, beautiful generating function that goes back to Euler. And by today's standards, it is trivial. The generating function of this. So there's no closed form for P of n, but there is a nice, beautiful product formula for the so-called generating function. In other words, 1 minus q, the reciprocal, 1 minus q squared, 1 minus q cubed, done that. There is no closed form formula for P of n, but there is something almost as good. There is an asymptotic formula, a beautiful asymptotic formula that enables you to compute P of a million very, very fast. It is so good that a few 5 of 10, I don't remember, these 5 terms will give you a floating point, things with decimal, but if you know the error, you can find the exact number. So this is this. How did Rademacher arrive at this seminal formula? He did an infinite, like we learned in calculus, partial fractions, he did an infinite partial fraction decomposition for this. So you can factorize it by roots of unity and do it, and then you write it as infinite partial fraction. So 1 minus omega q to the omegas are all the root of unity. There's possible powers, blah, 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 doesn't matter. So that was the starting point of the proof, and then how he derived this seminal, famous formula that got George Andros to be a mathematician. The Hardy-Ramanujan-Rademacher. Rademacher was a great improvement on the previous version of Hardy and Ramanujan. So he did an infinite. Then, in a seminal book, classic book, by Hans Rademacher, Topics in Analytic Number Theory, which was published posthumously. Towards the end, Rademacher had a dream. Suppose you only look at this finite things you can give to your calculus students. It's a finite. And now it's a generating function of partitions into integers with at most capital N parts, or equivalently with the largest part, capital N. And you do the partial fraction decomposition for this truncated part. You get some numbers, and now that with Maple, you can get them. Quite a few for n up to 10, and of course it's not so easy even with Maple if you're not clever, because you have to factorize completely over the cyclotomic fields, blah blah blah. But you can do it up to 10 easily. You get some numbers in the partial fraction depending on capital N. And Rademacher conjectured that if you take these numbers that show up in the partial fraction decomposition of the truncated version of this Euler product, the limit they get to the famous Hardy-Ramanujan-Rademacher numbers that show up in the infinite things. It was a very possible conjecture. very plausible conjecture. And Rademacher strongly believed it. And Rademacher completely by hand computed up to 5. Up to n equals 5. And he got pretty close to his conjectural one. Sorry, he didn't have much evidence. And people believed it! And George Andrews assigned it as a PhD problem to one of his students. Of course, he couldn't do it. He did something analogous, something completely analogous, interesting, but not the same thing, a very special case of analysis. And George Andrews tried to prove it many times. And other grammar mathematicians told me private communication, Ken Ono tried to prove it. All these people who I know about, and probably many people I don't know about, tried very hard to prove them, to prove this conjecture. It didn't go to them, it may be false. Rademacher, the grammar mathematician, he probably, no way, he could have made it false. And it's so plausible. Here's something true for little n, the capital N. So if you let capital N to infinity in the partial fraction decomposition for n, it's reasonable that at the limit you get the infinite partial fraction decomposition for the infinite case. Very plausible. And people believe in it, and people try to prove it very, very hard. And George Andrews in 2003 wrote a long article whose main point was to try and prove this conjecture. And as a historical curiosity, even George Andrews makes minor mistakes. George Andrews made a major mistake by refusing a priori to even consider our beautiful disproof of a major open problem that had been open for almost 50 years, just because we, as we claim in the title, we didn't have a rigorous quote-unquote proof. It was a non-rigorous proof, but it was a proof nevertheless. And he tried here very hard, and then propagation of mistakes. He copied the Rademacher values of some value. And even Rademacher in 1969, before he died, so he had calculators, we could ask somebody to do it. There is a mistake in the calculation here. And George Andrews believed Rademacher so much, he just copied and pasted it. But he didn't have copy and paste them. He just copied it by hand and let the secretary type it, the same mistake. So it has some minor errors, nothing else. And then Rademacher gave the values of the constant up to n equals 5. And George Andrews in 2003 already had Maple, Mathematica, big computers, and lots of students. He did it up to 8. He continued and saying, he continued this table up to n equals 8. And still, the conjecture made even more plausible. When you go up to n equals 8, you get even closer to the Rademacher values. But then, about a year ago, Drew Sears and I found a disproof, certain disproof. Non-rigorous disproof, but certain disproof. First, we had a computational breakthrough. Rademacher by hand went up to n equals 5. George Andrews, with a computer, I'm sure, went up to n equals 8. And we computed these values up to 900 terms. And we had a plot, and that was non-trivial. We had a nice new algorithm, a non-trivial algorithm to crank out, non-trivially. If you do it by brute force, you won't go very far. That's why Andrews only went up to 8, if you do it by completely straightforwardly. We had a nice new algorithm, interesting on its own right, to crank out the first 900 terms of this partial fraction composition up to this. If nothing else, we have 900 new theorems. Every fact is a theorem, a Gibbs theorem, a thing that no human, no Andrew Wiles, or Kaiser Perman can find the value with 900. Of course, we cheated, we used a computer, but still, and not that brute force by a computer, we did it. And we drew it. And here's a paper. We plotted it. This sequence is a family of sequences, many sequences. But the first sequence that came up, here it is. Here it is. First it goes this, then it goes this, then around at n equals 24, it gets ever so close to what Rademacher conjecture is a limit. And then if you go to 100, you start dropping. And then go up, and then down, and then up, and then down, and through the roof. It's completely oscillating. And it's of exponential growth. It's a major disproof. If you go up to 900, and of course, it's possible, they will continue, logically possible, not any physically possible, not common sense possible, but it's logically possible, and that could be John Andrews and other narrow-minded people's retort. It's possible that the group keep oscillating up to a million, zillion, zillion, and then starting behaving, and slowly but surely going to the Rademacher value. I think that this is impossible. Not unlikely, impossible. Because the way it's defined is not that complicated. And once we have this oscillating behavior, and we have a specific, very, very good fit, is the period is oscillating like this, the period is 32. And we characterized the local maxima, the peaks, and the valley, the exact location up to 900. So I don't think it would be too hard to get a rigorous disproof by proving this alternative statement that obviously would imply that it does not converge. It's an oscillator thing. But it won't be terribly interesting. The Rademacher conjecture would have been interesting if it were be true. A rigorous proof of Rademacher conjecture would have been interesting. It would have given us lots of insight. But the rigorous disproof would not give us any, be completely futile, possibly technically difficult exercise, but will not give us any new insight, or not major numerical insight. You never know, by doing a difficult problem, sometimes you can get unintended insight. I'm not ruling this out. And it could be a nice exercise, possibly with computers, to get a computer assisted or generated proof of our modified conjecture that shows this. But frankly, it's a different project that may or may not be acceptable or suitable for the prestigious proceeding of medical science. That's a different problem. I'm not judging. But the disproof, even though it's non-rigorous, is much. It's a major increase in mathematical knowledge, in number theoretical knowledge. Here is a famous, rightly famous, great number theorist who made a conjecture that many people believed and tried very hard to prove. And some people made half-baked partial things. And here we come and give convincing proof, a physical proof. And it's especially disappointing, it's a proceeding of Academy of Science, not of mathematics. And you should be interested. It's an increase in mathematical knowledge that is very significant. A major conjecture of a major mathematician that has been open for 40 years had been shown to be correct. But John Andrews, being a member of his time, by a priori rules, rejected it. It's not even negotiable. As long as it's so in the title, almost certainly, meaning not rigorous, he even didn't consider it. And he recommended it that it's still interesting, not for the prestigious proceeding of science, National Academy of Science, but maybe for experimental mathematics, maybe for massive computations, maybe for other lesser genres. If it were been my way, I would have said, forget it, journals. I don't need any more publications. I can just post it on the archive and on my homepage, like many of my papers. I don't care about the approval of the adults approval. But Drew Sears, my collaborator, he is not yet tenured. Now he's tenured, but at the time he was not tenured yet, and he had to worry about his CP. So, because of him, we tried a second try. We saw maybe with the current views of early 21st century mathematics. They are not yet ready to publish it in the highbrow, fancy, pretentious, ambitious journal. But there are many journals in the sea. So a natural second thing would have been a journal that is considered good for the promotion and tenure committee. Good but not great. Math of computation. The original name of math of computation was